Hello everyone and welcome back to my channel. LangChain allows us to chat with our files and quickly summarize them. With just few lines of code, we can combine large language models with our document and quickly summarize them and search for answers. On today's video, we are going to talk about summarization with LangChain. We will build a summarization applications from scratch using LangChain and OpenAI. We will talk about basic prompt template, different type of chains such as stuff, MapReduce, and refine. And we will end this tutorial by talking about LangChain agents. We will start by showing you how you can summarize a few paragraphs, and then at the end I'm going to show you how you can summarize an entire book. By the end of this tutorial, you will be an expert in building summarization application using LangChain and OpenAI. So, without any further delay, let us get started. Alright guys, before we start, I just want to inform you that I'm going to leave a link in the description of this video for the Jupyter notebook that I'm going to use. So please feel free to download this notebook and follow along with me. So let us now start building our first summarization application using LangChain.
Let us first talk about setup. First, we are going to install the required packages. We have two options to install it. Either by creating a requirement.txt file with the name of the packages or by using the pip package manager to install it one by one. I have already installed the required packages, which are LangChain, OpenAI, Python environment, unstructured, PDF to image, PDF miner, and PDF miner.six. We will explain each package as we write our code. Second, we have to create a .env file to store our environmental variable. In this .env file, we are going to store all our API keys and configuration. For this tutorial, I have already created a .env file and I stored my OpenAPI key. Let us now first creating our first summarization application using LangChain. First, we are going to load the environment variable from a .env file. This is where we would store out the OpenAPI key and other configuration setting. The override equal true parameter in load.env tells the load.env function to override any existing environment variables that have the same name as the variable in the .env file. This is useful if you want to make sure that the values in the .env file are always used, even if there are conflicting environment variables set in the system. For example, if you have an environment variable called OpenAI API key that is set to a different value in the system, the load_.env function will override the system value from the .env file. This ensures that the OpenAI API key environment variable is always set to the value that is in the .env file, regardless of what the system value is. Now we are going to use LangChain to create a conversational AI application. We will import the chat OpenAI class from the LangChain.chat_models module and the AI message, human message, and system message classes from the LangChain.schema module. So from LangChain.chat_models module import chat OpenAI from LangChain.schema import. We have AI message, human message, system message. The chat OpenAI class is used to generate text responses to user messages. The AI message, human message, and system message classes are used to represent different types of messages that can be sent by the AI application or the user. The AI message is a class that represents an information message that is sent from the AI system. The human message is a class that represents a message that is sent by the human interacting with the AI system. And finally, the system message is a chat message representing information that should be instruction to the AI system. Now we are going to create a new instance of the chat OpenAI class, and we will call it LLM. So we'll have LLM equal to chat OpenAI. This represents an instance from the large language model. The chat OpenAI class takes two arguments, the temperature and the model name. The temperature is a parameter that controls the randomness of the large language model responses. A temperature of 0 will produce the most deterministic responses, while a temperature of 1 will produce the most random responses. The model name is the name of the large language model that will be used. We will set in this example the temperature to 0, and the model name we will set it to GPT-3.5-Turbo. The GPT-3.5-Turbo model is a large language model that is trained on a massive dataset of text and code. The model is known for its ability to generate creative and informative text, as well as its ability to hold conversations that are both engaging and informative. Now, let's run the code and make sure it's working. Yes, it's working. The instance of chat OpenAI class, this one, the LLM, can be used to generate text, translate languages, write different kinds of creative content, and answer your question in an informative way. Now we are going to define a variable called text message. That will contain the text that we want the LLM to summarize. I have already prepared a sample of a sample text for the definition of the large language model application, and please feel free to try different text messages. The value of the text messages is a long string that describes the concept of memory in conversational AI system. Here we are going to use triple quotes, which are called duck string, because it will allow us to enter multi-line string. This is useful for entering text that is longer than one line. Again, here the text I'm using is for the definition of LLM application as an example. Next step is to define a list of two messages. The first message is a system message which is an instruction to the LLM from the user. The LLM will use this instruction to generate a response that is tailored to the user need. I have already prepared a sample message as well. I'm just gonna copy and paste it. So in this example, the system message is telling the large language model that the user is a highly skilled writer who specializes in copywriting and summarization. This information will help the large language model to generate a more relevant and informative response. It is important to note that the system messages are not always instructions to the large language model. Sometimes system messages can be used to provide context or background information to the large language model. For example, a system message could be used to tell the large language model what the current topic of conversation is. The use of system message is a way to control the flow of a conversation with a large language model. By using system messages, user can ensure that the LLM is generating responses that are relevant to their need. The second message that we are going to use is a human message. So we'll have a human message and the content is equal to have. Also, I have already prepared a sample message which I'm going to copy and paste. So the human message represents a message that is sent by the human or the user interacting with the AI system. Here we are instructing the LLM to provide us with a summary of the text message that we defined above here. This letter F is used to create an F strings. F strings are a new string formatting mechanism that was introduced in Python 3.6 and are a more concise and convenient way to embed Python expression inside a string literal for formatting. In the code, the F string is used to insert the value of the text message into the string. This is done by using the text message syntax. The text message syntax here tells the Python interpreter to replace the text message placeholder with the value of the text message variable. The use of F string makes the code more readable and concise. It also makes the code easier to debug, because the value of the expressions that are embedded in the F string are evaluated at runtime. So let us run our code and make sure it is working and there is no syntax error. Yes, it is working. One last thing, let me just add here after of copywriting and summarization, just to define a clear role. Now in this step we are going to ask the LLM to generate the summary by passing the message object. First we will create a new variable called summary, and we will make it equal to LLM messages that we created before here. This means that the summary variable is assigned the result of calling the LLM function on the message variable. The LLM function will take the list of messages, the system messages and the human messages as input, and return a summary of the messages. The LLM object is an instance of the Chat OpenAI class that we created here, and it has a method called generateSummary that can be used to generate a summary of a list of messages. The generateSummary method takes one argument, which is the message list. The message list is defined as a list of system message and human message object here that represents the messages that has been exchanged in a conversation. The generateSummary method will generate a summary of the messages in the message list and return the summary as a summary object. Now let us print the summary object. The summary object has a property called content that contains the text of the summary. This means that the summary.content is used to get the content of the summary. The print statement, let's now run our code and make sure it's working. It's going to take a little bit of time because it's contacting Chat OpenAI. The print statement prints the content of the summary variable. The content of the summary variable, as we can see here, is a string that contains a summary of the messages. Here we can see that we got a short summary of the text as instructed by the human messages. So here is the original text that we entered, and here is the summary message that is returned from the LLM model. One last note before we end this part. There is one thing I just want to make it clear. It is important to be aware of the text lengths that we are passing, because the LLM model have a context length and cost more for longer text. So in order to know the text length, we are going to use the getNum token, which is LLM.getNum get underscore num underscore tokens text message, and let's run it. We are using 253 token. We use this method getNum tokens to determine the length of the text. Then the length of the text can be used to determine how long it will take to process the text or how much it will cost. So here we are getting the number of tokens used during the summarization process. Tokens are just the basic units of text or code that a large language model uses to process and generate summarization. Tokens, it can be character, word, subword, or other segments of text or code depending on the choosing tokenization method or scheme. So that's it, guys. Congratulations. We created our first summarization application using LangChain and OpenAI. I was explaining slowly the step because it is our first application. In the next part, I will be moving a little bit faster. So let us now create a summarization application using prompt template. Alright guys, in this second application, we are going to create a summarization application using prompt template. We will generate a summary of the text message we defined in the previous application and then translate it into another language. We will use the dynamic prompt offered by LangChain to summarize the same text. Please note that this method is restricted to summarizing text that, together with the summary, has a length lower than the model maximum allowed number of tokens, which is approximately around 4096 tokens. The prompt template class allows defining reusable templates for generating responses from the AI or the large language model. And this prompt template that we are going to define can be used in any other AI application. Alright, so let us start writing our code. First, we will import the prompt template class from the LangChain module. This will be used to define templates for generating responses. Also, we are going to import LLMChain class from the chain module of LangChain. From LangChain. This LLM chain will be used to change the LLM model with the prompt template. Now we are going to define a new variable called template. We will define a template string that contains the text that will be used to generate the prompt. Let me now write the code and I will explain it to you. The template string includes two parameters, text and language. The text placeholder will be replaced with the value of the text variable, and the language placeholder will be replaced with the value of the language variable. Again, here we will use a triple quote to allow us to write in multi-line. In the template, we are going to instruct the AI model to generate a short and concise summary of the provided text, and then translate the generated summary to a specified language. Next, we are going to create a prompt template object. But first, what is a prompt template object? It is an object that is used to define a prompt for a large language model. The prompt is just a piece of text that is used to instruct the large language model to instruct text. So, we will create a prompt using a prompt template object. And we are going to initialize it with two arguments. The input variable and the template string. The input variables are the variables that will be used to fill in the placeholder in the template string here. So they are going to be the text and the language. So here we are going to pass text, language. This prompt template object can be used to generate a prompt for the large language model. The prompt will be generated by replacing the placeholder in the template string with the values of the input variable. And the template here, we are going to use the template that we have just created here. Please keep in mind that the input variable defines what values must be provided each time the template is used. And in this case, it expects a text and language. With that, this prompt template can be used to summarize any text and translate it to any language just by providing those two inputs. Let us now create an LLM chain object. As we said before, an LLM chain object is an object that is used to chain together a series of steps that are performed by an LLM. The steps in the chain can be used to generate text, translate tasks, or perform other tasks. First, we will create an LLM object and initialize it with two arguments, the LLM and the prompt. The LLM object is the LLM that we created before in the previous application and will be used to perform the steps in the chain. The prompt template object is a prompt that we will be used to instruct the LLM. So here I'm going to use the prompt that we just created. Let us run these two code cells to make sure everything is working fine. It's working, and here also it's working. So the LLM chain class wraps the low-level API of an LLM and provides high-level methods like chain.generate_response or chain.run. This abstracts away directly dealing with the LLM API and keeps prompt engineering separate. The LLM chain manages conversation across multiple prompts by maintaining state and history of the chat. So this line creates an LLM chain instance using the provided LLM and prompt template, which can now be used easily for generating conversational responses. Now we will call the run method on the LLM chain to generate text, and it is run by passing it a dictionary of input variable. So we will have summary is equal to chain.run, and we are going to pass a dictionary of input variable. And if you remember, the input variables are text and language. For the text, I have to pass the text that I want to summarize, which we defined in our previous application, which was called text message. And for the language, you can choose any language of your own that you want to translate to. Let us, for example, choose French. So we will pass a dictionary with the input parameter required by the prompt template. Text contains the actual text to summarize, and language is specified here as French. Let us run the code cell and make sure it is working. It's going to take some time because it's going to connect to Chat OpenAI to summarize the text and then translate it into French language. And it's finished. Next, let us print the summary of the text and the translated summary and see the result. As you can see here in the result, the text is summarized and it is translated to French.
So congratulations again, you created your second application of summarization with LangChain and Chat OpenAI. Please try to work and choose different template, create your own custom, choose different text, different language, and check the result. So let us now start building a summarization application with LangChain and StuffDocumentsChain. Alright, now let us start building our third summarization application. We will be using another summarization method called stuffing. The StuffDocumentsChain is a pre-made chain provided by the LangChain that is configured for summarization. It uses a T5 model behind the scene. The benefit is we don't have to configure the prompt, LLM, and so on. It provides an out-of-the-box summarization solution using LangChain. The pros of this method is that it makes a single call to the large language model, and when generating a response, the large language model has access to all of the data at once. The cons are that most large language models have a context length, as we said before, and for large document, this will not work because it will result in a prompt that is larger than the context length. So to summarize, the main downside of this method is that it only works with a smaller piece of data. Once we are working with multiple pieces of data, this approach is no longer feasible. Anyhow, let us start writing our code. First, we will import the required function. This imports the load summarized chain function from the LangChain summarized module. LangChain.chains contains pre-made chains for different tasks like summarization, Q&A, search, and so on. Load summarize underscore chain provide an easy way to load a chain ready for summarization. The second line imports the document class from the LangChain.docStore.document. The document class represents a text document and metadata that can be stored in a document store database like Elasticsearch. The chains handle interacting with the large language model behind the scene, and DocStore integration allows building things like search retrieval powered by the large language models. For the purpose of this application, I have created a text file in the same directory of this Jupyter notebook. The text file contains an article that is about convolution neural network as an example of large document. I have already prepared a code for reading text from a file using Python, which I'm gonna copy and paste here since it is not the purpose of this tutorial to learn about Python. Now we will read a text file and create a document object to represent it. The first line will open the text file in the current directory for reading it and encoding it. f.read, this reads the entire content of the file and stores it in the variable text. The second line of code will create a list with a single document object, and the document is initialized with page underscore content equal text. Let us run our code and make sure it is working. And for the template, I'm going to use the same template that we created here. I'm just gonna do a small modification. I don't need the translation, and here I just need the text, just for the purpose of showing you how the StuffDocumentsChain works. After that, I'm going to create the chain. So we'll have a chain equal load underscore summarize underscore chain. We will define the LLM model, and then the chain underscore type is equal to stuff. The prompt is equal to prompt, and verbose is equal to 2. We are using the LLM object that we created before, and the chain type is stuff. We will use a stuff chain which summarizes by extracting key details from the text. And the prompt is the template we created before, and verbose equal true so that it will print the logs. This load a StuffDocumentsChain tuned for summarization using the provided large language model. Alright, let us run the code. Now let us run the chain and generate the summary. So we'll have summary is equal to chain.run, and we will pass the variable docs, which we store the content of our convolution neural network text file. So let us run the code and see the result. As you can see here, it's printing not only the summary, but it's printing the log. In case you don't want the log, we can change verbose here to false. Let us run this code cell again, and let us run the chain.run again so that we don't see the log, we just see the output summary. And now if you want to see the content of summary, we will use print summary. Let's run it. And this is a summary. As we can see, we have a very short summary which contains the key details of the convolution neural network definition that is in the text file. And that is what the StuffDocumentsChain uses. It uses the key details inside the text in order to generate the summary. Alright, and by this we end this part. Let us now start using summarization with LangChain using MapReduce. In this part, we are going to build a summarization application with LangChain using MapReduce. LangChain provides a MapReduce chain that can be used for summarization using a MapReduce style workflow. This allows summarizing a collection of documents in a MapReduce style architectures. The benefits are summarize large collection of documents and distribute work across mapper and reducer, and customizable by writing our own map and reduce functions. So in summary, MapReduce chain provide a scalable summarization solution by leveraging the MapReduce principle. This method will split the document into small chunks that fit within the token limit of the model. It will first summarize each chunk, and then it will get a summary of the summaries. MapReduce uses two prompts, an initial one to summarize each chunk of data, and then a different prompt to combine each summary into the final one. The pros of this method are that it scales to a larger document, and the call to the LLM on individual chunks are independent and therefore can be in parallel. And the cons are that it requires more calls to the LLM model than the StuffDocumentsChain that we saw before, which uses only one call to the large language model. It also loses some information during the final combining call. And also please note that if you are on the free plan from OpenAI, you can get into some issues because this method will make multiple API calls to OpenAI, and the free accounts are limited to 3 requests per minute. So you might need to add a credit card in the billing section in order to run this example. Depends on how large the document you are using. So let us now start building our application. First, as usual, we will import the required function and classes. The new import now here is the recursive character text splitter. We will import the recursive character text splitter from the LangChain text splitter module. The recursive text splitter is used to split long text document into smaller chunks before feeding to the language model. Some key points to mention here is that first, language model have a maximum input size that can process. Large documents need to be split. Recursive character text splitter split text into chunks based on the maximum character length. It uses a recursive algorithm that ensures sentences are not broken in the middle during splitting. The smaller chunks can be can then be processed separately by the language model. And finally, output chunks from the splitter are typically merged back together after processing. I'm going to use the same text file that I used here in the previous document, but without loading it into the docs. It's working. And if you want to check the number of tokens that we are going to use, we can check by using llm.get underscore num underscore tokens text. And we are going to use around 2022 tokens. Now we will create a recursive character text splitter object, and we are going to use it to split the text into chunks. So we'll have text underscore splitter is equal to recursive character text splitter, and it takes two parameters, chunk underscore size equal and chunk underscore overlap equal. The chunk size parameter specifies the maximum size of each chunk, and the chunk overlap parameter specifies the number of characters that should overlap between adjacent chunks. For this example, we are going to use a chunk size of 5000 and a chunk overlap of 20. The chunk size of 5000 means that each chunk will be 5000 characters exactly, and the chunk overlap value of 20 means that consecutive chunks will overlap by 20 characters. Then we are going to make a call to the create document method on the recursive text splitter object. So we'll have chunks is equal to text underscore splitter dot create documents text, which is our text file here. The create document takes a list of text as input and return a list of chunks. The chunks are creating by splitting the text into chunks of the specified size with the specified overlap, which are 5000 and 20. Then the chunk variable contains a list of document objects representing the chunks. So this allows splitting a long text into manageable chunks for the language model using the recursive character text splitter. Let us run our code and make sure there is nothing wrong with it. Okay, name is not defined, so maybe I have some spelling mistake. Let's run it again. Import. I did not run the importing here. Yeah, now it should work. So if I run this again, yes, it is working. And if we want to check the length of our chunk, we can use length. We can say length chunks. So we have around 3 chunks, total of 3 chunks.
Now let us load the summarize chain and run it on the chunk of text. The summarize chain is a chain that is used to summarize text. So we'll say here it's equal to load underscore summarize underscore chain. The load summarize function takes 3 arguments. The LLM object, which we created before in the previous application. The chain type will have chain underscore type is equal to map underscore reduce. And the verbose flag, verbose is equal to false for now. If you want to check the log and see every step that's happening, you can set it to true. We are going to use the LLM object that we created before. And for the chain type, we will specify map underscore reduce. And for the flag, we are going to set to false because we don't want to see the logs. Now let us run the chain on the chunk of text. Okay, so we'll have here summary is equal to chain dot run, and we are going to run it on the chunk of text which we created here. The run method takes a list of chunks as input and returns a list of summaries. The summaries are generated by running the chain on each of the chunks of the text. This method will assign the list of summaries to the variable summary. Now we can use the summary variable to access the summaries of the chunk of text. Alright, so this leverages MapReduce principle to summarize large texts that have been split into smaller chunks. The chaining handles the complexity behind the scene. So let us run our code here. It's gonna take a little bit. Alright, now it's finished running, so let us print as a summary and check the summarized text. Run, and as we can see here, it's working. We have summarized our text here, which was about the convolution neural network. It was a very long article, and we use here the chain type MapReduce. If you want to access the template string from the prompt template object, we will write the following code. We will say chain.llm underscore chain dot prompt dot template run, and we run it. This will show us the first prompt template that was being used on the chunk. And if you want to check the another prompt template that has been used after all the summarization of easy chunks, then you have to write the following: chain dot combine underscore document underscore chain dot llm underscore chain dot prompt dot template, and run it. This code is accessing the prompt template used by the combined document chain inside a LangChain summarization workflow. Alright, by this we reach the end of this summarization application where we use LangChain using MapReduce. Alright, so let us now start building summarization application using the refined combined document chain. Alright guys, now we are going to build a summarization application using the refined combined document chain. But what is the refined combined document chain? So let us give a brief introduction about it, and then we will start writing our code. The refined combined document chain in LangChain provide a way to do multi-step summarization using refinement. The workflow is: first, it will generate initial summary for the first chunk. Then it will summarize the first summary along with the second chunk. Again, it will summarize the second summary combined with the third chunk, and so on. The fourth step, which is the last step, it will consolidate the refined summaries into final summary. So the refined combined document chain is more sophisticated summarization technique than the reduced summarized chain, because it's able to generate more accurate and informative summaries, because it will take into account the context of the text when generating the summaries, and this is very important. The benefits are: first, the initial summary provides context for refinement. It can pull more relevant context from the previous document, and it may be less lossy than the MapReduce document method. The disadvantages: it requires many more calls to the large language model than the StuffDocumentsChain or the MapReduce chain. And the calls are not independent, which means that they cannot be parallelized, like in the case of the MapReduce chains, because it will wait for the first summary or the previous summary, and then it will combine it with the next chunk and generate the summary. So the calls are not independent, so it cannot be run in parallel. Let us now start building the summarization application. The first step, as usual, we will import the libraries. The only new library is the unstructured PDF loader. This unstructured PDF loader class is a class that is used to load PDF documents into a format that can be processed by an LLM, large language model. It will take the PDF document as input and return a list of chunks. These text chunks are created by splitting the PDF into chunked to text. Now let us create an unstructured PDF loader object and loads a PDF document into a list of text chunks. So we'll have load is equal to unstructured PDF loader. It will take a PDF document as input and return a list of text chunks. So I'll have here the path to the PDF document. And as a real example here, I will load an article about the graph neural network, because currently I'm working on a research paper about privacy and security of machine learning. And I will use a graph neural network to apply privacy and security. And I have a lot of research paper to read. So I am using LangChain along with refined document chain to summarize this article. This article is located into the same directory of this Jupyter notebook, and feel free to use any PDF document you have. Next, I'm going to call the load method on the object in order to access the text chunks and will assign it to the data variable. So I'll have data equal loader.load. Let us run our code and make sure it's working. First, let me just run this code for the import. It is okay. And for this one, unstructured PDF loader is not defined. Maybe I have a spelling mistake. Yeah, spelling mistake. Loader is not defined. Loader is not defined. Ah yeah, spelling mistake as well. So I was having spelling mistake. I was calling it load here. It should be loader. Okay, so let's run our code and make sure it's working. Yes, it's working now. Now we will print the text content of the first page of the PDF document. So I will have print data to access the first page underscore content. So we will get the first text chunk from the data list by using data, and we specify 0, and then we will use the page content that contains the text content of the page. Let's run our code. Yeah, as you can see here, this is the first page. This is the content of the PDF. As you can see, it's a huge file. Next, we will create the text splitter and split the document in chunks of 5,000 characters and for chunk overlap for 50. So we'll have here text underscore splitter is equal to recursive character text splitter chunk underscore size is equal to 5,000 and chunk underscore overlap is equal to 100. And then we will call the split document method on the recursive character splitter object. So we'll have chunks is equal to text underscore splitter dot split underscore document data, which we define here. The split document method takes a list of text and return a list of chunks. Again, the chunks are created by splitting the text into chunk of the specified size here, which is 5,000, and the overlap, chunk overlap here, which is 100. So let us run our code. I have a spelling mistake here, so it is split documents, and it's working. And if you want to check the length of chunks to see how many chunks we have, we write length chunks, and we have 13 chunks. Now let us load refined summarized chain, the refined summarized chain, and run it on the chunk of text. So we will have a chain is equal to load underscore summarize underscore chain. Again, the load summarize chain takes 3 arguments: the LLM object that we defined before, and then the chain type, which we are going to specify as refine, and the verbose flag, which I'm going to set to false. Next, we will run the refine summarize chain on the chunks of text. So we'll have output underscore summary is equal to chain.run, and we will pass the chunks that we created before. So the run method takes a list of chunks as input and returns the summaries. Now the output summary has a list of summaries. So let us now run this code. It's going to take a little bit of time to generate the summary because it's making the call to the large language model. As we said before, the chain type refine calls to the large language model are not dependent, so we cannot are dependent, which means that we cannot run them in parallel. So that's why this method will take a longer time to run. So now let us print the output summary. So we'll have print output underscore summary. And well done, guys. You have created a summarization application using the refined chain type. Now in the next and final part, we are going to create a summarization application using the LangChain agent. In this last part, we are going to create a summarization application with LangChain agent. But first, let us give a brief introduction about LangChain agent. Summarizing with LangChain agent is a technique for summarizing text that uses a chain of agents to generate a summary. The agents in the chain are responsible for different tasks in the summarization process, such as extracting important information from the text, generating a summary, and then refine the summary. The LangChain framework provides a number of different agents that can be used in the summarization process. These agents include, but not limited to, first, an extractor agent. The extractor agents are responsible for extracting important information from the text. They do this by identifying key phrases, identifying sentences that are important to the overall meaning of the text, and then identifying sentences that are relevant to the user's query. The next type of agent is the generator agents. These agents are responsible for generating a summary of the text. They do this by combining the information that was extracted by the extractor agent into a coherent and concise summary. And the other type is the refine agent. These agents are responsible for refining the summary. They do this by removing redundant or irrelevant information from the summary, and by making sure that the summary is grammatically correct and easy to understand. This LangChain framework also provides a number of different ways to chain the agent together. This allows you to customize the summarization process to your specific need. For example, you could chain the agent together in a way that first extracts important information from the text, then generates a summary, and then refines the summary. Summarizing with LangChain agent is a powerful technique that can be used to generate a high-quality summaries of text. The framework is very flexible and customizable, which makes it a good choice for a variety of summarization tasks. To summarize, here are benefits of the summarization with LangChain agent. First, it can generate high-quality summaries of text. It is flexible and customizable, and it's easy to use. But it has some limitation. It can be computationally expensive because it needs a lot of resources to extract and summarize the text. It can be difficult to tune the parameter of the agent, and it can be difficult to interrupt the result of the agent. So let us now start building the application. As usual, first we will import the required libraries and classes. Here we are going to import the initialize agent and tool classes from the LangChain.agent module and the Wikipedia API wrapper class from the LangChain.utilities. The initialize agent class is used to initialize an agent, and the tool class is a basic class for all the agents in the LangChain framework. The Wikipedia API wrapper class is a class that is used to access the Wikipedia API. Let us run the code. Next, we will create a Wikipedia API wrapper object. So we will have Wikipedia is equal to Wikipedia API wrapper. Now we will create a list of tool objects. So we will have tools is equal to tool. The tool object is a class that used to represent an agent in the LangChain framework. The tool object has three attributes: the name is equal to, and the function, and the description. The name attribute is a string that specifies the name of the agent, and the function attribute is a function that is called when the agent in the running state. The description is a string that provides a description of the agent. So for the name, we are gonna use Wikipedia, obviously, Wikipedia. And for the function, we are going to use Wikipedia.run. And for the description, we are gonna using Wikipedia for getting information. So when constructing the agent, we need to provide it with a list of tools that it can use. These tools are ways that an agent can use to interact with the outside world. It's like a toolkit for this agent. Let's run our code, and it's running. Let us now initialize an agent. So we will have agent underscore Wikipedia equal to initialize underscore agent. The initialize underscore agent takes 4 arguments: the tools that we created in the previous step, and the LLM object which we created before in a previous application, and the agent. So we'll have agent is equal, and the verbose flag, we'll set it equal to false for now. Alright? For the agent, we are going to use zero-shot React description. So we'll have here zero-shot React description. It's a type of agent in the LangChain framework that is used to generate descriptions of reaction to prompts. This agent is trained on a dataset of prompts and description, and it can generate description for prompts that it has never seen before. It is a powerful tool that can be used to generate a creative and informative description of reaction. It is also very easy to use, and it can be customized to generate descriptions for different types of prompt. With all these benefits, this agent has some limitation. It can be computationally expensive to train the agent, and it can be biased depending on the dataset that it is trained on. And this agent can be difficult to interrupt, as it is not always clear how the agent generates its description. Let us run the code. Now let us run the Wikipedia agent. We will use the run function, so we'll have output is equal to agent underscore Wikipedia dot run. The run function takes one argument, that is the prompt,
And the prompt is just simply the text that is used to generate the output. For our example, we will pass a prompt which is, please provide a brief summary of what is graph neural network. Let's just run the code. It's going to take a little bit of time to generate the summary, and it is done. Now, in order to access the summary, we'll just simply type here print output. Great. By this, we have created a summarization application using LangChain agent. And here, if you want to check the steps that has been done to generate the summary, we can set verbose to true. And let's run the output again. And then here you can see how the agent is working. And we see here, it specified the action is going to Wikipedia and the action input is a graph neural network. And now here it's getting the information and we can print the summary again. And that's it, guys, for this application for building a summarization application using LangChain agent. Alright, guys, that's all for this video. I hope you learned something new about building summarization application using LangChain and OpenAI. If you have any question, please leave a comment below. And if you enjoyed this video, please give it a like and subscribe to my channel for more content like this. See you in the next video.